the slope of the bed, is it? Then again, the cross-sectional area or the shape of the open channel may vary. It can be triangular, rectangular, trapezoidal, but in pipe, it is uniform along the section line. Then there is a surface roughness. Pipe networks are made up of smooth surfaces, wherein your open channels are having the different surfaces along with the different depths. In pipe network, there will be a constant pressure head along the line of the pipe, but in open channel the head may vary. Okay. Again, day before yesterday we have seen about the laminar and turbulent boundary layer conditions. So in that we have seen the velocity distribution in pipe network is uniform as it is maximum at center and minimum at the surfaces, because at surfaces we are having the stress. Okay. But in open channel, there is a maximum velocity occurs at the distance below the water surface, and shape of the velocity profile is totally depend on the channel roughness. Where your channel is more rough, there you will get the least velocity, and where the channel will become smooth, you will get the maximum velocity. Okay. Now, so with this, you are clear with the open channels. Very common basic difference between the open channel and a pipe section is your pipe network will run under a hydraulic pressure, wherein your open channel will run under a gravitational force by the using the slope provided in the channel bed. Okay. So now we will move to the open channel section. So first of all, what are open channel? So open channel are nothing but which are not completely enclosed by the solid boundaries, and they have the free surfaces subjected to the atmospheric pressure, or the flow of liquid through a channel with a free surface will be termed as your open channel, where there is a no pressure at the upper side of the channel. Then your channel will be termed as a open channel, means it is having a free surface. This free surface of the liquid is subjected to a definitely an atmospheric pressure. Hence, open channel flow can also be defined as your flow of liquid through a passage at an atmospheric pressure. Is it? Now your pipe running half full or not running full volume of its total diameter, then it will be again considered as your open channel. The flow in open channel will take place due to basically because of its gravitational force that is achieved by providing a channel bed or a slope bed. Okay, you can see I have shown few shapes for the open section. This may be your rectangular section, a trapezoidal section, a triangular section, even a pipe which is not running through will be considered as a open channel. हेलो हाँ अच्छा एक मिनट सर आई सर एक मिनट में फुल स्क्रीन करती हूँ आती है क्या देखिए आई आई दिख रही है सर ओके सो आई थिंक नाउ स्क्रीन इज विजिबल टू ऑल ऑफ यू yes so these are your basic shapes for the open channel. Okay, it may be rectangular, triangular, trapezoidal, or a pipe which is running half full. Okay, because it is free to atmosphere. So an open channel will have a slope, a definite a bed slope, then there will be a free surface. Okay. Now the flow in the open channel or the flow in the flow of the liquid through the open channel can have the several types of different conditions. The flow in the channel will be categorized on the basis of so many different types of classifications. Okay. So basically there are two types of channel section, maybe one may be natural open channels and another one will be artificial one. In natural channel, we will consider your rivers, your lakes. Is it in artificial, your drains, culverts, sewers, tunnel lines, your pipelines, your barrages? These all will consider in your open channels. Then, open channel may be classified according to the type of flow which is running into the open channel. Okay, so it may be steady, unsteady flow, uniform, ununiform, laminar, turbulent, then critical, subcritical, and supercritical. So we'll see one by one. So yesterday we have seen that what is steady flow? Steady flow is a condition when the pressure, velocity, and density will not change with respect to time, and that flow will be considered as your steady flow. Okay, wherein if your velocity, pressure, and density will change according to the time, then that flow will be considered as your unsteady flow. Then there is uniform flow and non-uniform flow. Then uniform flow will be the flow in the channel is said to be uniform if the given length of a channel, the velocity of flow, the depth of the flow remain constant. The various parameters like velocity, depth, cross-sectional area of the channel will not change as with respect to its length, then that channel will be considered as your uniform flow. And in non-uniform flow, the flow parameters like velocity, depth of flow, etc. will do not remain constant. It means they will keep going on changing. Then that flow will be considered as your non-uniform flow. Okay, so for the uniform condition, like dy by ds will be equals to your 0 or dy by ds will be equals to your 0. But for non-uniform section, your dy by dx is not equals to 0. That is your depth will change with respect to length. Okay. Then we will move to the just observe this figure. What is happening? See over here. At the left hand side of the flow condition, there is a uniform flow. You can observe this that it is having a constant depth, a constant velocity, but suddenly there is a obstruction into the velocity or into the path of your flow. So what is happening? Suddenly, abruptly, there is change in the velocity, change in the depth. Also, there is a change in the slope of the bed. So your constant flow of water acquires a haphazard way or the disturbed way. So what is happening? Your flow has become the non-uniform flow. Its velocity has been changed, its energy has been changed, and it acquires the turbulent types of flow. So this is nothing but the uniform flow and non-uniform flow. Again, see over here, water is coming out of the reservoir. At the reservoir, it is at rest condition, then suddenly it acquires a velocity. So at a glance, it is changing its velocity quite rapidly. So it will be termed as your rapidly varying flow. Then again it acquires a uniformity. Then again there is an obstruction. Because of that obstruction, there is a backfall of water and there is suddenly downfall of that water. So within a short duration of time, it acquires a higher velocity. Because of that, your uniformly varying flow converted to a rapidly varying flow. Okay. So here in non-uniform flow, there are two types of flow, that is the gradually varied flow and rapidly varying flow. So what is gradually varying flow? When your flow parameters like velocity, when your flow parameters like velocity, pressure, depth of the flow will change abruptly over a small length of the channel, then it will be termed as your rapidly varying flow. And what is gradually varying flow? When your flow parameters like pressure, velocity, depth of the flow will vary slowly or will vary gradually over a long length of the section, then it will be termed as your gradually varying flow. Okay, so the time duration in gradually varied flow is quite large as compared with your rapidly varying flow. The changes in the flow characteristic will be in a rapid manner in rapidly varying flow, and these will be gradual when we will talk about the gradually varying flow. Okay, both are the types of non-uniform flow. Now, next, third type of classification of the liquid is based on the Reynolds number, that is termed as your laminar flow and turbulent flow. In case of pipe section, the laminar and turbulent flow has been uh, given by the Reynolds number, and there the boundaries are laminar. We will call a fluid or a liquid in laminar condition when your Reynolds number is in range of 0 to 2000, is it? But in open section, we will call it as a laminar flow when you are having a Reynolds number of 500 or lesser than that. Then it will be a turbulent flow if you are having a Reynolds number of more than 1000. And if your Reynolds number is in between 500 and 1000, then we will call it as transitional flow. Okay. Then there is fourth type of classification, that is based on screen is visible or not. Okay, then there is a subcritical, supercritical, and critical flow. Okay. Now, the flow characteristics are defined as subcritical, critical, or supercritical flow on the basis of Proud's number. Now, Proud's number is ratio of your viscous force to gravitational force. Is it? So, Proud's number plays very important role while designing any type of channel because it has the component of gravity. Okay, so whenever you are designing a channel, especially an open channel, in that case your water should flow under the gravity. Is it? So in that case, it is very much essential to find out your Proud's number because Proud's number is ratio of inertial force to the gravitational force. Now it is V divided by square root of GD. Now all of you know that if it is lesser than 1, then your flow will be subcritical. If it is equals to 1, then your flow is said to be critical. And if your Proud's number is greater than 1, then your flow will be supercritical. Okay, but what is the condition between subcritical and supercritical? When your water is not in a constant motion or it has the haphazard motion type of thing, it is not in a stable condition, then that condition will be termed as your subcritical flow. Here you can see on the left hand side of the section there is a varying velocity, a varying depth section, and a varying slope bed also. Is it? So here the water is in the subcritical condition. The Proud number is greater than that. But water cannot stay into the subcritical zone for the longer period. It will always try to be in a stable condition. So the subcritical condition will be converted to the supercritical as it will try to move on in a uniform flow with a uniform velocity. So this section is your supercritical section where your cloud number is greater than 1. Okay, so subcritical is a section or a junction of water where your water is not in a stable condition. It is in an unstable condition. And supercritical is a condition where your water is in a stable condition. In between subcritical and supercritical, there is a point when your water just transit between subcritical to supercritical, and that will be your critical section. Okay. Okay. So basically, the flow in an open channel will be classified on four basic conditions or four basic flow types, that is your steady and unsteady flow, uniform non-uniform flow, turbulent non-turbulent flow, and last one is critical, subcritical and supercritical flow, which is based on the Raoult's number. Okay, then there is a section condition as we have seen here. Okay, subcritical, supercritical and critical condition. Then we will move to the characteristic of uniform flow. Now we will derive an equation. Okay, just assume this open channel. Now observe this open channel. In this channel, we have assumed one water surface which is at the distance of z from the datum line. Okay, which is inclined to the datum line. So the distance of the water surface or the bed of the section is at a distance of z from the datum line. Okay, then there is a layer of water on that datum surface, that is your at a distance of y. Then there is one more imaginary line, and that is nothing but your potential head. It is an imaginary line which will give you the head of the velocity, because water is running at a velocity of v. Okay, so that head is termed as your v1 square or v square by 2g. So consider one head, a horizontal head over which your bed is inclined, which is at a distance of z. Then over that bed you are again having water layer and its potential, that is a velocity potential, that is your v square by kg. Okay, so in this, see, there will be a slope of that bed. So the slope of the channel bed will be termed as your s0, or you may assume that slope of channel bed as a sb. Okay, then there is a slope of that water level or the water inside the channel. So assume that slope of the water surface as your SW. Okay. Now see, now consider two sections into this uniform flow channel. At section 1, you are having a characteristic like A1 as area, B1 as velocity, and Z1 as data. At section 2, you are having B2 as velocity, A2 as area, and Z2 as determinant. Okay, so when you will apply a Bernoulli's theorem at both the section, so you are given with the, you will be come up with an equation. Okay, so as we know, as per the energy equation, as per the Bernoulli's equation, your total head at both the section must be equal. Is it? So from that equation, you can say that energy at first section must be equal to your energy at another section. Is it? That is your z1 plus y1 plus v1 square by 2g must be equal to z2 plus y2 plus v2 square by 2g plus its energy loss or the head losses. Okay, if you will neglect the head losses, then your equation will reduce to y1 square plus v1 square by 2g must be equal to y2 plus v2 square by 2g, because the datum are equal. Okay, so the energy at both the sections will be termed as your specific energy, and these energy must be equal as per the Bernoulli's theorem. Now we will move to, we have seen the Proud's number. That what is Proud's number? It is the ratio of inertial to gravitational force. We will move to here how we can find out the discharge or velocity in the open channel. Okay, now there are two formulas we have seen in the five sections for the uniform flow, and both equations are widely used for the open channels also. They are your Chase's equation and the Manning's equation. Chase's equation is your V is equals to C square root of Rs, and Manning's equation is your V is equals to 1 by n r to the power 2 by 3 s to the power 1 by 2. Okay, so by Chase's equation, you can find out your discharge is area into velocity. So area into velocity will be c into square root of rs. And again, by the means of your Manning's equation, you can find out your discharge as it is reduced. You have to put your velocity in continuity equation, that is q is equals to area into velocity. So you will get a reduced equation, that is 1.486 by n into a into r to the power 2 by 3 s to the power 1 by 2, where s is your slope of the bed, v is your mean velocity, n is your Manning's constant, and r is your hydraulic radius. R will be calculated as area by perimeter. Okay, now okay, see this. Now we have equated energies at both the sections. Okay, so the change in energy, or you can say the total energy drop, will be calculated as E1 minus E2 divided by S0 minus SW. That is, the E1 is energy at section 1 and E2 is just energy at section 2. E2 is energy at section 2 and S0 is your slope of bed and SE is your slope, SW is your slope of water. Okay. Then we have to find out the various characteristics of the open channel. Now, when you have applied Bernoulli's equation at section 1 and at section 2, is it? So, you are given with the formula, that is dy by dx. When you will solve that Bernoulli's equation, so you will get an equation that dy by dx must be equals to s0 minus s divided by 1 minus Raoult's number square, or 1 minus f square. By means of this equation, you can find out the depth of the channel over the particular length or horizontal length of the section. Okay, where S0 is your slope of bed, SW is your slope of water, 1 minus Proud's number. Proud's number will be calculated as V divided by square root of GD or GL in case of open channel. Okay, in open channel, when your section is uh, quite wide, in that case, you can directly take your depth of water as equals to your hydraulic mean radius. That is, R can be approximately equals to your depth of water. Okay, so by replacing Y by R, you will get a modified equation for wide rectangular channel, that S by S0 can be replaced by Y0 by Y to the power 10 by 3. In what condition? When it is mentioned that your channel section or a rectangular channel section is wide and having a uniform flow condition. Okay, then we will move to our next topic, that is your specific energy. Now, before going to derive few equations or few formulas by means of specific energy or specific energy curve, we will go through the definition. Now, we know that specific energy is nothing but a summation of datum head, datum head, water head and potential head. That is Z plus H plus V square by 2G. Okay. If your height of the channel bottom is same as your height of the water, that is your channel bottom is horizontal, then your energy equation will be minimized to E H plus V square by 2G. Okay. So ES, that is specific energy, is given by H plus V square by 2G for the horizontal beds. Okay. So the specific energy is your energy, length or head relative to the channel bottom. It is expressed in terms of kinetic energy and potential energy. Your kinetic energy is nothing but your V square by 2G and potential energy is nothing but your H. Okay. Here the Bernoulli's equation, which is originated from the volume analysis, is used to describe your specific energy relationships. In the form of Bernoulli's equation discussed, assume flow is your incompressible and steady equation. We are using here three energy components in Bernoulli's equation, that is pressure, velocity and a datum head component. Now in open channel what we are considering, that one of the section component is open to the atmosphere. The pressure term between two points has the same value and it is therefore ignored. Okay, because we are saying that it is open to atmosphere. So when you will apply a Bernoulli's theorem on both the sections, so what is happened? Your pressure term will be eliminated or it will be cancelled off. So we will have only two heads, that is the kinetic head and a potential head. So if your specific energy and the velocity of flow in the channels are low, the depth of the flow can be determined. Okay. Now when you are eliminating your pressure term, so you will have an equation in terms of two existing terms, that is a potential and kinetic head. That is E is equals to kinetic energy plus potential energy, that is nothing but your H plus V square by 2G. Okay. So now we know that your discharge is nothing but area into velocity. Okay. So your velocity will be discharge per unit area and area is nothing but B into H in case of rectangular section. So replace that. So you will get velocity is nothing but small q by H. And what is small q? It is discharge per unit width, that is q divided by V. So replace this V is equals to q by H in specific energies formula. So you will get your E is equals to H plus q square by 2G into H square. Okay. So before going to derive few more formulas, we will just observe this graph. Now see this graph. When your specific energy is totally potential energy, so you will get an horizontal graph where Es is equals to your H. Okay, you can see a horizontal line which is inclined at an angle of 45 degrees. Then when your specific energy is totally kinetic energy, that is E is equals to B square by 2G, then you will get a graph which is a second degree parabolic curve horizontal to y-axis and x-axis also. Okay, yes, you can see that curve over here. And when you will plot specific energy as a function of both potential energy and kinetic energy, then you will get in a curve which is below the potential energy line. Okay. Now see, when you are having a specific speed, a specific energy of particular quantity, so you will get two depths for that. Okay? If supposed to be you are having your energy over here, so you will have a H1 value and an H2 value. So these two values for a particular specific energy will be termed as your alternate depths. For every energy you will have two depths. One is your lower energy, another one is your upper alternative energy. So these two depths will be termed as your alternative depths. But where you are having a minimum energy, at that point you are having only one depth and that depth is termed as your critical depth, and that critical depth is associated with always your minimum energy. Okay. Again, when your flow is subcritical, so you will get a Proud's number which is lesser than 1. But when your Proud's number is greater than 1, your flow is supercritical. Okay. So when you are having a higher number of highs, in that case your flow is not in a stable condition. So when your water flow or your flow of water will come into the stable condition, your Proud's number will become equals to 1 and it will require a constant velocity and energy specifications. Okay, so again we will move to this. Now see, your critical depth has a Proud number equals to 1, is it? And it corresponds to the minimum energy of flow, which can possess a given discharge. Now all flows are not critical. Okay, so below 1 we are considering it as a subcritical and above 1 we are considering it as a supercritical. Okay, in subcritical flows the flows are definitely they will be deep, the velocities are slow or you may call it as a constant. Okay, but in case of supercritical flows the depth of the section will be shallow. Okay, they are not as such as deep as subcritical flow and the velocities are the quite fast. Okay, uh, supercritical flow will have a low potential energy and a high kinetic energy. Okay, okay. So here we have replaced your discharge as discharge per unit width, that is small q, and you are getting an equation for specific energy as h plus q square by 2g into h square. Okay. When your specific energy is minimum, your depth is critical. Okay, E minimum is always associated with HC, that is your critical depth. Okay, so E is equals to HC plus Q square by 2J into HC square. Okay, here you have substituted HC, so your energy will be E minimum. So when you will solve this, you will get an equation for the Hc, that is critical height, that is q square by g to the power 1 by 3 or cube root of q square by g, where small q is nothing but your discharge per unit width. Okay. Again, when you will derive an equation for the minimum energy, so you will get it as a 3 by 2 of the critical depth. This replace, substitute 3 over here and 2 over here, so you will get E minimum as 3 by 2 of critical depth, and critical depth will be calculated as q square by g of to the power 1 by 3. Okay, so these three formulas, that is first one is your specific energy is v square by 2g plus h. Second one is your critical depth can be calculated as q square by g, small q square by g to the power 1 by 3. The next one is your E minimum is 3 by 2 of critical depth. Okay, there is one more formula, that is critical velocity, which is given by square root of g into critical height, that is hc. Here you can see that critical velocity can be calculated as g into hc to the power 1 by 2 or square root of g into hc. So these are four formulas which are widely used by solving the questions for the open channel. Okay, so we will go through quickly one question, one numerical. Just read out this. A water flows in a rectangular channel having a Manning's constant as 0.017. A channel slope is given, that is S is given 1 by 7,000. Width of channel bottom is 5 meter and depth of flow is 1.1 meter. Okay, open channel है, so depth of flow दिया होगा. हमको क्या निकालना है? Discharge in the channel, specific energy and critical depth. Okay, discharge in channel is nothing but your Q, specific energy is E, critical depth is your HC. Okay, so write down all the given values. Okay, N is given to you, that is 0.017. Okay, it is a rectangular section, so your area will be B into D. So B is 5, D is your 1.5. Then in open channel, you always go with the weighted perimeter, not the perimeter. Okay, weighted perimeter is nothing but when the side of the channel which is touched by the water, okay, or which is in contact with the water. So here, except your upper surface, all three boundaries are in contact with the water. Okay, so how will you calculate weighted perimeter? That is simply B, that is the channel bottom, plus 2 of D, both side of depths, plus 2. Okay, so you will find out your weighted perimeter by P is equals to B plus 2D. Okay, so weighted perimeter आ गया हमारा 7.2 मीटर. Then hydraulic mean radius is area by perimeter. Area is B into D. Weighted perimeter is B plus 2D. ये भी आ गया 0.764. Then you have to find out discharge. So discharge is your A into B. Okay. Now to calculate discharge, you are having two formulas. One is your Chase's formula. Another one is your Manning's formula. Is it? So constant की तरफ जाएंगे हम लोग. If you are given with the Chase's constant, so definitely you have to use your Chase's formula. Here you are given with the Manning's constant, that is n. So you have to use the formula of Manning, that is 1 by n r to the power 2 by 3 s to the power 1 by 2. Put all the values which are given to you. You will get your velocity as 0.587 and discharge will be given as area into velocity. So discharge is coming out as 3.228 meter cube per second. Okay. Second thing which you have to find out, second quantity, that is specific energy, is nothing but depth plus v square by 2g. So d plus v square by 2g or h plus v square by 2g. D is given 1.5. Then v square by 2g. Put all the values. You will get your specific energy as 1.12 meter. Then critical depth. Critical depth will be calculated as small q square by g to the power 1 by 3. Small q will be calculated as discharge per unit width. Put all the values. You will get your critical depth as 0.349 meter. Okay. In this case, if supposed to be you have to find out critical velocity, then again it is square root of g into hc. You are having hc. Here you have find out bc is nothing but your hc and it multiplied by g, so you can find out the bc also. Okay. Then in open channel, in open channel, there are different types of water profiles for the gradually varying. Okay, these profiles are classified on the basis of the depth of water. Okay, now there are three types of depth of water into the channel. First one is your critical depth. Critical depth is a depth where your Froude's number is equals to 1. Then there is a normal depth. Normal depth. Normal depth is the depth phi n, which is the actual depth of the water, or you can call this as a depth where you will have your NDL line. That is your normal depth line. Okay. So whenever we have to decide that which type of water surface profile is this, we have to assume all three surfaces. First surface is your channel water. Okay. Second line will be of your CDL line, that is critical depth line, which will be associated with your critical depth. The third line will be your NDL line, that is your normal depth line. Okay, that will be associated with your YN, that is normal depth. Okay, so once you have fixed all three lines, then we have to check that which type of profile is this. If supposed to be that profile is of first type, that is your YC and YN are greater than your water depth, then it will be considered as your mild slope. Then for critical slope, your normal depth and critical depth should be equal. Then if the normal depth is greater than, or you can say it is infinity compared with the critical depth, then it will be a horizontal slope. Then if supposed to be your normal depth is lesser than your critical depth, then it will be steep slope. And if you are having a critical depth at lower height and normal depth, uh, even at a lower depth, that which cannot be predicted, or you can say which cannot be shown into the figure. Okay, so in that case it will be your adverse slope. Adverse slope, it means a slope, a inclined slope, where your water has to move in a forward direction, but it is moving into the backward direction. Okay, it is having a negative slope, so that will be considered as the adverse type of slope. So these all channel profiles or the water surface channel profiles will be decided on the basis of two parameters, that is NDL line and CDL line, and which type of water curve or which how the water is actually flowing out of that NDL line and the CDL line. Then we will move to one of the interesting topic of hydraulics or in open channel, that is the most economic channel section. Okay, now what is the meaning of economic? It is, you can say it as a cheap in layman language, or you can not cheap but a minimum value or a minimum cost of construction. Okay, so economic section is which it is a section which is having a maximum discharge for a given cross sectional area and the bed. So those parameters are very important while designing most economic section, that is cost of construction should be least or minimum, and discharge, that is the Q, should be maximum. So it is a channel which is having a maximum discharge for given area or for the given cross sectional area of the section. Okay, so this channel section can be of trapezoidal type, rectangular type, circular type, or triangular type. So, which type of characteristics should it have? It gives maximum discharge for a given cross sectional area. Then it should have a minimum weighted perimeter. Minimum weighted perimeter, it means it should have a minimum cross sectional area. Then again, it should involve the lesser excavation for the construction. Okay, so we will see one by one that what are the different conditions which should get satisfied for design of the rectangular for design of the most economic channel section. Okay, so first section is your rectangular section. One thing we have seen in definition, that your perimeter should be minimum or weighted perimeter should be minimum. So weighted perimeter should be minimum with respect to its depth. Okay, so we have to differentiate your weighted perimeter with respect to D, and for the minimum condition their derivative should be equal. Okay, so more for most economic channel section, there should be dP by dd must be equal to 0. Okay, so for first section, when we will go with the rectangular section, so we will get this condition that your width must be equals to 2 into depth. That is, B should be equals to 2 into depth, or depth should be equals to half of the width. Okay. So for most economic section of rectangular channel, hydraulic radius must be equals to the half of the depth of the flow. Okay, that is M, or you may denote it as a R. M or R must be equals to D by 2, or a rectangular channel which is having a hydraulic radius halves of the depth. Okay, or its width should be as double as its depth. Then second one is your circular section. Okay, so here you can see when you will differentiate your dp by dd with respect to 0, here in this case you have to differentiate your perimeter with respect to the angle theta, and you have to equate this with 0, so you will get a most economic channel section condition. So here you can see for maximum discharge through a channel or a circular section, you will get a maximum discharge when depth of the water is equals to 0.95 times the diameter of circular channel. Okay, so the total depth of the water must be equals to the 0.95 times the diameter of the channel. Okay, and the velocity through a channel of circular section is maximum when the depth of the water is equals to 0.81 times the diameter of circular channel. Here you can see that D is your diameter of channel and D is the depth of the depth of the water. Okay. So the velocity through the channel of circular section is maximum when the depth of water is equals to 0.81 times the diameter of circular channel. Okay, then we will move to our next section, that is your trapezoidal section. So for trapezoidal section, here you can see there are two conditions, that is your hydraulic mean radius should be equals to d by 2, or the angle of inclination of the sides of the trapezoidal section should be at 60 degree. Okay, it means for most economic section of trapezoidal channel, the hydraulic mean depth should be half to the depth of flow, and again the for most economic trapezoidal sections, its sides should be inclined at an angle of 60 degree. Okay, then there is one more section, that is the triangular section. Triangular section is missed by me, it has not been included here. So again, triangular sections you can note it down. For triangular section, just write down two conditions. The most economic section of triangular channel is one which has its sloping side at an angle of 45 degree with the vertical. Okay, then again for the triangular section, its angles its angle should be inclined at 45 degree with the vertical. Okay, so we will see one example, and here I have included an example of trapezoidal section. Okay, a trapezoidal section is given to you, and you have to find out definitely a discharge for, and you have to design it by most economic channel condition. Okay, so for most economic channel condition, we are having two conditions, so we will apply those two conditions over here. So you are given a slope, that is one horizontal to two vertical. So and will be ratio of horizontal to vertical, that is 1 by 2. Okay. Bed slope is also given. This is the side slope. Okay. The side of the trapezoid. Then bed slope is 1 by 1500. Okay. So area of section is your 40. Then Chase's constant is given, that is C is equals to 50. Okay. So we have used here one condition for most economic channel section. By means of that, you will find out the discharge. Okay. So you will get your D, that is the depth of water, as you have to just rearrange this equation. Okay, by rearranging this equation you will get an equation in terms of d, and put that equation in terms of d, and equate that equation in terms of d from the area, as area is given to you, and you will get your depth value. Okay, then you have to find out your discharge. So discharge is equals to a into c square root of mi by using a Chase's constant. Okay, so you will get your maximum discharge for given economic trapezoidal section is your 80 meter cube per second. So next topic for the today lecture is your hydraulic jump. Okay, now we have seen that what is uh, varied flow. Okay, in varied flow there are two types of flow, that is the gradually varying flow and rapidly varying. When your water is varying at gradual speed, what is happening? It is varying its velocity, depth, and slope of the bed at a longer section of the channel, or at the longer span, at the longer time. So there will not be a sudden change into the characteristic of water. But when we are talking for the rapidly varied flow, there will be sudden change into the velocity, into the depth, as well as into the other characteristics of the channel along the length of this section. So, because of the rapid change into the characteristics of this flowing water, there will be formation of jump from one end to another end, and that jump will leads to your loss in energy, or either a dissipation in energy. Okay, so in simple language, what will be a hydraulic jump? Just observe this figure. Here, at left hand side, at your downstream side, your water is coming. Suddenly there is an obstruction. Because of that obstruction, there will be sudden change into the velocity and the pressure and the cross sectional area of the channel. Because of that, there is a sudden rise into the water height. Is it? So that is nothing but your jump. So what is hydraulic jump? It is a phenomena that is frequently observed in open channels such as rivers, canals, spillway or weir, which will dissipate excess amount of energy. Okay. So hydraulic jump is formed when your high velocity liquid is discharged into a zone of lower velocity, creating an abrupt increase in the depth. Hence, we can dissipate huge amount of energy. This energy is nothing but a conversion of your potential energy into the kinetic energy with some energy loss in the form of frictional or turbulence formation or eddy formation or the heat or noise formation. Okay. Now see, when jump forms, now there are so many types of jump. Okay, you can see over here the jump is classified on the basis of Proud's number only. Okay, if you are having a Proud value between 1 to 1.7, it will be a pendular jump. If it is between 1.7 to 2.5, it will be a weak jump, and varying up to, if your Proud's number is greater than 9, then it will be a strong jump. Okay, so you can find out your Proud's number as v by square root of gt, and once you will have the Proud's number value, you can classify your jump. Okay, now what is the use of hydraulic jump? See here, before the jump, we will assume our energy, your depth of water as y2. And after the jump, we will assume your depth of water as y1. Okay, so see here, or y1 or y2. What will be your hydraulic jump depth? It will be simply y2 minus y1. That is, y2 is depth after jump and y1 is depth below jump, before jump. Okay, your water is in the subcritical condition. Once your hydraulic jump happened and your water will acquire the stable condition. That is, and at the upstream side over here, your water is into the supercritical condition. It is having the Proud's number greater than 1. But before the depth y1, over this spillway, your water is in the unstable condition. It is having a Proud's number less than 1. Okay. So once a jump is happened in between y1 and y2 depth, there will be somewhere a critical depth. Okay. So these y1 and y2 are nothing but your conjugate depths, or you may also call it as a sequent depth. Yes, your specific energies are not equals to minimum, but in between these depths there will be a critical depth, that is at C, where your specific energy will leads to minimum. Okay. Now, hydraulic jump may have few uses. Sometimes what happens, because of the unnecessary disturbance, unnecessary turbulence, there will be huge amount of energy creation into the jump. So that energy may destroy your already made structure. So to overcome or to avoid that destruction, there can be a hydraulic jump, so that we after jump we can dissipate that energy and can use into the some another good work. Then if you have to measure the discharge out of that channel, again in that case hydraulic jump is useful. Okay, then if you have to add few chemicals or few other type of admixtures into the water, then again a hydraulic jump is useful. At treatment plants, at sewer plants, where you have to treat water, hydraulic jump is again useful. Okay, so there is an equation to find out the hydraulic jump. Okay, just assume this as a this, observe this figure. Here, your depth of water before the jump is y1 and depth of water after the jump is y2. Okay, and the length between y1 and y2 is your length L. Okay, so slope of bed is equals to 0. We have assumed the slope of bed as 0. Okay, now here We have neglected the frictional losses. Again, you have considered a unsteady flow and the incompressible flow. These are the assumptions while calculating the equation for alternative depths or equation for the hydraulic jump. Okay. Now, as we know, what is momentum equation? Momentum equation is nothing but change in mass and change in volume must be equals to the total energy stored into the section or total pressure force stored into the section. Now, total pressure force stored into the upstream side will be equals to your total pressure force, that is P1, and total pressure force stored on the downstream side of the section will be your P2. Okay, so when you will equate the pressure forces by the momentum equation, that is F1 minus F2, that is the loss in pressure force must be equal to the change in momentum. Okay, so change in momentum is your rho q v2 by v1. So we have just equated here, and when you will solve this equation by substituting all the other forms of equation or other terms, then you will get an equation in terms of y1 and y2, and this is your equation for, here you can see that y1 is equals to y2 by 2 in bracket minus 1 plus square root of 1 plus 8 2 square. This is your equation to calculate the hydraulic jump depth or the sequent depth. Okay. Here Proud's number is nothing but your v divided by square root of g2. In some books you may also find out it as a y2 is equals to y1 by 2 minus 1 plus square root of 1 plus 8 fr1 square. Okay. If you are replacing y1 by y2, then here again replace your f2 by f1. So by using this equation, you can find out the other forms of Proud's number, the other forms of the conjugate depth. If you are given with the depth 1, then you can find out the alternative depth by 2. If you are given with the Proud's number, then you again can be find out with the velocity and the length of the channel. Okay. So in open channel, there are 5 to 6 main formulas by which you can solve all the numerical type problem. Number 1, which is related with your which is related with your hydraulic jump, that is y1 is equals to y2 by 2 in bracket 1 minus 1 plus square root of 1 plus 8 fr1 fr2 square. Okay, then second one is your critical depth, that is q square by g to the power 1 by 3. Then there is critical velocity, which is square root of g into hc, that is acceleration due to gravity into critical depth. Then there is specific energy minimum, that is E minimum is equals to 3 by 2 of critical depth, that is hc. Okay, then there are two formulas to calculate the uh, velocity by means of Chase's formula and by means of Manning's formula. Chase's formula is v is equals to c square root of mi. Manning's formula is here 1 by n r to the power 2 by 3 s to the power 1 by 2. Okay, then we have deal with the most economic channel sections. In most economic channel section, especially four channel section uh, are given, or you have to deal with the four channel section. First one is your rectangular section. For that, your uh, hydraulic mean radius should be half of the depth of the flow, or the width of the channel should be twice as depth. The second one is your trapezoidal section. Again for trapezoidal section, your n should be equals to d by 2 and theta must be equals to 60. Then third one is your circular section. For circular section, your diameter of the channel must be equals to the 0.95 times the depth of the water. Okay. Then third one is your, sorry, fourth one is your rectangular channel. Sorry, triangular channel. For triangular channel, your uh, for a most economic triangular section, the sloping sides should be inclined at an angle of 45 degrees. Okay. So here we have covered all topics of the open channel. Okay, so hope you have enjoyed this, and just try to solve few more problems related with the open channel, which are based on the these equations only. Okay, thank you.